Oh, yeah. So hello, everyone. Thanks for the invitation. I'm very happy to be here. So I'm going to be sharing with you this recent work with this gentleman. And so I'm physically at GGI. I wish I could have come to Minnesota. And there's one important reason why I'm going to tell you later. So my outline is this. I know at least one of you, Jane, who has seen this a version of this talk before, but I promise you there's new material. I'm not gonna be repeating. So I'm gonna give an introduction on Muon G-2, and then I'm gonna summarize the previous papers on G-2 Muon and then implications for Muon Collider program. And then the new material is on what happens at hadron colliders and also some indirect signals Muon collider for different scenarios that I'm going to be defining in a second. Okay, so before this, so I just wanted to mention an epic trip, but not this one. That is certainly more epic than the one I'm going to tell you. Is so you know about this one, all the details from the magnet moving from Brookhaven to Fermilab. But I just wanted to mention this epic trip. That is the trip I took to get the vaccine shot. I was in Colombia. Barranquilla is the city next to the Caribbean coast. So when the country opened vaccination for people my age, I could not get the vaccine at my city. So I started in a very long road trip to actually be able to get the vaccine, and it was quite an adventure. I will tell you the details if I were at Minnesota and over dinner. I'll tell you all the details. But then, so for not wasting your time with this, let me go ahead. So in the first slide, I just want to define. So we talk about this G factor as a measure of the strength of a magnetic moment. And there's a prediction on, if you do relativistic quantum mechanics, of 2. But then deviations from 2 is what we call the anomalous magnetic moment, or what you see some papers where they call this, for example, muon or electron anomaly. So they don't refer to the fact that there's a mismatch between theory and experiment. They refer to the deviation from 2 as the muon anomaly. Yeah. So the status of the measurement, we got it in a very nice talk by Ida the day of the announcement in April. So right before the announcement, the situation was this: hadronic vacuum polarization calculations to NLO and NNLO. They go down to a point of precision where you see how the uncertainty in the leading calculation is already the same size, or roughly to the NNLO. So I guess this is a good stopping point for the hadronic vacuum polarization. So this is the total value they quote. This is from the theory report, the theory initiative. They put this report a little before the announcement of the Fermilab measurement. So this value they quote is from consensus in what they call the phenomenological calculations. So they do not include the lattice result because uncertainty is quite large, even though there is an exception. There's one group that calculates a value with an uncertainty actually similar to the one that they quote on the phenomenological calculations. So right before the announcement, we had this 3.7 deviation between the theory and experiment. And a little after the announcement, there was this paper showing improvements in what we call the hadronic light by light calculation. So they were able to bring down this, almost 50% uncertainty to, 14% in the calculation, concluding that the hadronic light by light cannot explain this discrepancy between theory and experiment. Then came the announcement from the first data set, which is already at the size of similar to Brookhaven. And the situation then show us that agreement between the two measurements, and a total of 4.2 sigma deviation with the standard model summary from the theory initiative report. Again, we have now this is the actual situation where there's the BMW calculation that then will say that basically there's no anomaly. The good thing about this is that in these three areas, we'll see improvements, or we'll hear news about these three different areas in the coming 1-2 years. In short time, we'll see updates from each of these areas, and we'll see how the situation evolves. So like improvements in lattice calculations between these different groups, also from the phenomenological calculations, and the experiment, we get more data. So then what comes now next in this talk assumes that after Fermilab runs, and after achieving the goals of bringing down both statistical and systematic uncertainties at this part per million, 140 part per million level, what happens is we see a 5 sigma deviation between theory and experiments, right? Then you start wondering what are the consequences of this, and this is what we did in the context of a Muon Collider program. So the first thing we did was to split the phenomenology here to see what are the ingredients that one need for the G-2. So we know it comes from this dipole operator, is a dimension 6 operator. It's a left-right operator. So you need a chirality flip, and because you need to contract the SU2 quantum numbers, you need some electroweak insertion here. So the way we split the phenomenology was this: so imagine that you can only this family of models where you only introduce one singlet in the loop, and that's it. In that case, so the chiral flip occurs proportional to the mu mass. So in these scenarios, the models are simple. You just have a singlet and that's it. But then the phenomenology can be tricky, because then you say, I produce this singlet, but then how does it decay? You need to make assumptions. Then for what we call the electroweak scenarios, is that now you can have in the loop particles that have charge. So which is now is a good thing or not. Well, it is a bad thing, because now the chiral flip can occur proportional to these new states. So you can push the scale of this new physics very, very high. But then when that's not the case, you have a particle that, at least one particle that has charge, and then you can produce it if you have enough energy. Yeah. So in this sense is that we thought this is very important for the Muon Collider, because you see, for the singlet scenarios, you have direct coupling to muons. You could just collide the muons, produce these singlets, and then having it recoil against something else, like photon, for example, and then look for it. But also is that with the Muon Collider, you can reach very high energy step too. So you can produce at least you worry about the lightest charge state in this electroweak scenarios. Yeah. So think about Muon Colliders. The idea is this comes and goes in waves. So the most recent wave of interest in the muon collider came, I would say, one of the main motivations was this is the proof of concept of the muon cooling, the muon beam cooling technology. That so so the muons, you get them from smashing protons on a target and let these pions decay and produce the muons, but then you produce them with a very ugly phase space that you need to now bring condense and to get a nice beam for collisions. So with this improvement or this proof of concept that from a year ago, so there's a renewed interest in the idea of a muon collider, where 10 dB it's understood as a reasonable goal for it. Yeah. So if you look at now the context of Singlet Scenarios, you have the G-2 loop, you have a new coupling and a new mass. The parametrics is more or less like this. The effect that you care goes with the coupling, and then as you increase the coupling, you increase the mass for a fixed value of the delta A. Yeah, so they scale up together like this. But then for couplings, you know that there is going to be some perturbative unitarity ceiling. So that puts also a bound on the masses of these singlets. So then in the case of vector currents, there's been efforts in seeing the consequences of these in current experiments, or even future proposals that I'm going to show later. And yeah, like for example, for the L mu minus L tau current, you could think of something like this, this trident production, and then what you find is that you constrain most of the parameter space, and at the low mass n, you do also, but it's just a matter of improving the measurements. Okay. So then, alternatively, you could also do this, some like Babar, collide electrons, produce the muons, and radiate the singlet. The singlet will decay back to muons, and then you look for this for this bump, and you constrain this region over here. So I guess it's complementary to this trident. Yeah. So when it comes to the question of how low is the low mass end of this in this type of figures, in the previous page or in this page. So this is a model dependent question. Yeah, but with this very light particles, you worried about cosmology. You can have extra radiation in the early universe that can spoil cosmology. But then, like, how low can this line go to the left? Can this line move to the left? Then it's a model dependent question. But this is, for example, this is just one example. Okay. So we would say that then the low mass n is very nicely covered. So we saw mostly up to here, this is for vectors, but then for the scalar, there's also proposals to how to do this with muon beam, the Fermilab NH64 type of muon beam, or this missing momentum experiment proposal. Okay. So yeah, so low mass n, very nicely covered. So now going to the upper mass end, and yeah, mostly for the scalar, but I'm putting the vector just so complementary. So what we did in those papers was to look at the collisions at a muon collider, produce the singlet, recoil against the photon, and what happens here? Then the singlet, as I said, can decay. You got to make assumptions about how does it decay. But the thing is that you can look for this. You can look for this photon. You're going to have a monochromatic photon whose energy is going to depend on the mass of the singlet. Yeah. So when in this region over here, where the singlet has sizable couplings, it is reasonable to say that it will decay back to 2 muons. But for the sake of completeness, and you could imagine that you also talk to some dark particle, then you will have only one photon and then missing energy. And then, so we were inclusive in our analysis, and just look at this photon that so for a given mass of the singlet, I expect this photon over here recoiling against missing energy or 2 electrons, 2 muons, even 2 quarks. Okay? So in that analysis, this is what we got. I'm showing you the mass of the singlets. The coupling is fixed by G-2. So as the mass increases, the coupling increases too. Yeah. So then I only worry about what luminosity do I need in this search of the monochromatic photon. Yeah. So then that means that below this line is what you can probe. So for the vector, yeah, you can probe pretty much everything that is left in the parameter space above what the low energy experiments can do. For the scalar, then yeah, there's a little gap, the lowest mass n, because here the coupling is very, very small. So the cross section start suffering.
Sorry, can I ask a question here? So just on the background, because I'm not so familiar with it, this scalar only couples to muons and nothing else, is that right? And so why doesn't it couple to the other fermions?
Yeah, so this is basically model building for perversity. Imagine that like the worst you can do, because if you couple to other things, then you will get more signals.
Yeah. But you're saying that the models are built just so that this thing just couples to the muon and nothing else.
Yeah.
But how is that arranged? Do you know?
No, and that's actually one of the objections that I'm gonna bring up for the next models.
Oh, okay.
Yeah, because at least for these singlet models, the upper bound in the mass is 1, 2, 3 TeV, right? But then when you include the other models where you have chiral enhancement, you could go up to like 100 TeV. But then yeah, you start asking yourself, wait, how can this be like in terms of like flavor and those kind of things.
Oh, okay, thanks.
Yeah, so thank you. This one out about is the luminosity goal for the 3 TeV muon collider. So this line is not just made up. This is a goal, right, for that collider. Good. So this is the other models where now you have this the chiral flip occurs proportional to the mass of a new object, and then yeah. So now the new physics can be very heavy. So you need to start making assumptions also. So how do you do this analysis of figuring out how heavy can this new physics be? You got new Yukawa. So here you got new states. We did a scan in these families of models where you look at models with representations up to triplets, for example. Representation of the objects inside the loop is important. And then models that will have charges up to 2. Yeah. So when you put all this together and you start asking for so how heavy can the lightest particle in the model be? Yeah. You get something like this, and this is the masses of the AB. I'm showing you just the example of the two scalar model and just one fermion. So 2 scalar, 1 fermion kind of models. So you see something like this. You get up to 100 TeV when you push the couplings up. to a perturbativity limit. Also, remember that, I don't know if I mentioned this, but that you can have a number of this new a number of copies of these new particles, right? From like a new flavor number inside this. So this flavor number for this plot is 1, but if you start pushing this up, then you push this scale up and up. Yeah. So there are many handles that can push this scale up. And so I want you to think about this as a surface. And so some ingredients that you include, like increase the number of BSM flavors, or if you increase the couplings, there's a limit for the couplings, but if you allowed for, like larger charges, what you're going to do is you're going to push the surface even to a higher masses. So this is just a cartoon, okay? But just because I'm going to be using the name max surface, so I just want you to remember that this is a surface. Okay? Yeah. So what we did in our paper, the one I'm summarizing, is now start asking questions about what happens with for example, minimal flavor violation, right? So if you arrange a flavor structure here for this type of Yukawas, you're going to have the muonic Yukawa. If you care about minimal flavor violation, there's going to be a tauonic Yukawa. Yep. So then you push the muonic Yukawa up to the unitarity limit, but then the tauonic Yukawa, there is a hierarchy between the two, there's a scaling between the two. The tauonic Yukawa will reach that unitarity ceiling first. So then there's like a factor of 17 different between the two. Yeah. So then in that case, the muonic coupling cannot be as high as previously suggested. So that will bring the max surface down. Another question you could ask is naturalness, because remember, this is a left-right operator, and there is a Higgs insertion somewhere here. Yeah. So now remove the photon. What you have is a Yukawa. You generate an effective Yukawa, and actually, in some of these models, you actually produce just the Yukawa, the dimension 4 operator with a coefficient in front that is very large. Now you have to what you do is that you take the 3-level Yukawa, Muon Yukawa, and you have to subtract these two numbers to get the muon mass, 0.1 GeV. So sometimes this subtraction is at the level of 10 to the minus 4, minus 5, it depends on where you are in the surface, in the max surface. Yeah. So if you care about all those ingredients, your flavor structure, your naturalness, and all this, what we saw is that the surface shrinks down to 10 TeV, which is good, right? It's the scale of the muon collider. But then, like these are just things that you could or could not worry about. So now
sorry. Yeah. The 10 TeV is a tuning of what in the muon mass? Did you say the tuning is what, 10 to the minus 3 or 4?
So you're asking what tuning will bring you down to 10 TeV?
Yeah. Yeah.
Oh yeah. So here is so we have tuning. There's a Higgs here for this model. There's a Higgs here. So you can have tuning in the muon mass and in the Higgs mass. So what we do is that you set 1%, both to 1%. Yeah.
I see. So you tune this contribution to the muon mass at the 1% level in order to get the low energy mass.
Oh no, the opposite. Like when you are at the max surface of 100 GeV, there is where the tuning is at 10 to the minus 4.
Oh, okay, yeah, okay.
Yeah. In order to then reduce the tuning just 1%, that is when the surface shrinks and you get the 10 TeV.
Yeah. Okay.
Yeah. Good point. So now the new developments are in the following directions. because right, we put this in the context of the muon collider discussion because at that moment was, you know, we saw this renewed interest. The muon collider, international muon collider collaboration hadn't formed yet. We started this discussion, and then, you know, so this was coming and this was relevant. But then, of course, the question that comes is the hadron collider. You know, what happens at the LHC? Yeah. So then, just to summarize, is that for the singlet, I'm coming back to the singlet models. Remember, you only have one singlet that talks to the muon, and that's it. Then this is the situation. You can look at this monochromatic photo, and then anything else, and you will see this. Okay. Now, at the LHC, the problem is that you need to first produce muons that then will radiate the singlet, and then it will decay somehow. Yeah. So there is this paper, I need to quote this paper, where they suggest that if you look at 4 muons at the LHC, well, actually, this is 4 electrons, is because in this model they care about the electron G minus 2. So then, so the constraint they get it's coming from there. But at least that there is, you know, hints that there is some region that can be probed. Okay. So and we do look for multiple leptons. In this case, this is 4 muon search, or for 4 leptons search. Yeah. So you just redo this search, but this time we did it with a different twist. We're adding two processes. Okay. So you can have either Drolian that is neutral, and so you get mu plus, mu minus via gamma Z. One of the muons is going to radiate the singlet, and the singlet will decay to 2 muons. You could also have this charged Drolian, where now the W will give you 1 muon, 1 neutrino, and the muon in the process will give you the singlet. The singlet will decay to 2 muons. So now we have 3 muon process with W, or 4 muon process with the gamma Z, scalar or the vector. Okay, and that's what these lines represent. The process with the W gives you a little larger cross sections. Standard model cross section is this is like total cross section. Yeah. So yes. So then, but then here you will look at the invariant mass of a pair of muons, and then so the cross section of the background is yeah, like for example, compared to the scalar, you know, 1 or 2 orders of magnitude larger. Sorry. But the thing is that's gonna be spread into different bins of the invariant mass, whereas for pairs of muons, whereas for the signal you're gonna see, you know, have a very beautiful peak. Okay? So this is what allows us to constrain some region of the parameter space. As you can see, now again, just the mass, the coupling is being fixed by G minus 2. So current LHC luminosity and high luminosity LHC. Below this line, this is what we have probed. Okay, we're combining searches with either 3 muons or 4 muons. One of them is relevant for low masses. The other one is more relevant for heavier masses and whatnot. But we put everything together, right? So now you might wonder, what is this line over here? Now the solid line is an optimistic scenario where the branching ratio to muons is 100%. So you only have that one coupling to muons, and that's it. But as the same thing I told you for the muon collider search, this singlet could talk to dark particles or something else. So then that's the dashed line, where now you are. So this is the most pessimistic scenario, and I should move this away. The most pessimistic scenario where now you take the minimum of the, you compare the width that you get from the coupling that you have and the masses that you have, and divide by some maximal width that we set to 30% of the mass. Yeah. So when you do that, so that means that there are some other channels for this scalar to decay, and actually for in the low masses, then the muon channel is not the one that's going to dominate. It's not going to dominate at all. So in that case, you get no constraints. Yeah. So now the real bound, of course, is going to depend on exactly the model you have, the flavor structure that you have, and all these the decay channels for the singlet. But it's gonna lie somewhere in between these two lines. Yeah. Sorry, I can drink water while if there's not a question. Yeah. Okay, yeah. So the real bound will lie somewhere in between these two lines. Yeah. For the vector, what we see is, yeah, in the optimistic scenario of 100% branching ratio, the LHC and the high Lumi will basically cover everything. Yeah, but I guess this is just complementary to the other searches, like for the Trident one. Yeah, good. Now, so something else you can do. So far we've been doing this part, the hadron collider part. But something else you can do is now electroweak precision constraints. So for example, in this paper, they care about flavor-specific singlets. They have a model with a scalar that talks only to the up quark, and the way to engineer that model is with the heavy quark. That when you integrate it out, is that you get this flavor-specific interaction. So you have this kind of processes. You're gonna modify Z decay to hadrons, but also you have mixing between these two particles. Yeah. So these lines over here is what you get from the electroweak precision test. So you get some constraint down to the 10 to the -4, but depending on the mass. So they do become relevant. But then the problem is that for this singlet, this is the singlet that we wrote, you then start wondering, okay, what are the UV completions for this? This interaction must come from somewhere, something that contract these SU2 quantum numbers. So you can think of different. So here we're engineering something similar to our friends from Pittsburgh with some heavy fermion that will mix with the standard model fermion. The heavy fermion here is the chi field. It's going to mix after the Higgs wave, and then you could do it with the left or with the right. You could do the mixing with the left or with the right. But you could also have more weird things where, like there's no mixing, but then there's a trilinear scalar coupling. So yeah, so here, then things start getting complicated because you have to do this exhaustive analysis that we didn't do. We just, but I can show you what happens with, for example, this type of examples, okay? So this, you integrate out the chi field, and then you get the GS coupling that you're gonna get. It comes like this, where m is the mass of the particle you're integrating out. So now, right, GS, then, so this mass, so this particle, sorry, that you're integrating now is gonna mix with the fermion. So you already start thinking, well, this guy must be heavy. And yeah, so this particle, sorry, this mass must be heavy. Actually, I think I have a slide for that. Yeah, you want this to be high, which means that then you have to push these couplings also up, and then but then at some point you're going to have a ceiling again for perturbativity for these couplings, and then so like there's a limit of what you can do for a given mass of this particle that you're integrating out. So yeah, so then in this family of models, we have here from the scalar UV completion, you have mixing as being important. For the vector singlets, there's no mixing, but even the loops are very relevant. I did not include the loops in the scalar because they turn out to be not relevant. What happens is that in the vector singlets, so for a given mass, the vector requires a larger coupling to get the U-2 with respect to the scalar. Like actually, this is like a factor of 3 or so. So yeah, so these couplings here, because these couplings are very large, the loop becomes relevant. And you get something like this ratio. So the quantity that I'm worried about is the decay of the Z to 2 muons compared to 2 electrons, right? So then remember that we're in the Nimer scenario where the new physics only to 2 muons. So this quantity is measured already as 0.3% level. So constraints from the vector comes from the loop, and constraints from the coupling from the scalar come from the mixing. And this is what you get. Let me see. Yeah. So then, so yeah. So this is the lines we had before this region from the collider search, and then we get these vertical lines that depend on the mass of the particle, of the heavy particle you're integrating on. Okay, the chi particle. Yeah. So then, to the right of this line is ruled out because to the line this mass will be too small. Yeah, and it will give you a mixing that is too big, and yeah, and the constraints on those are quite strong. Yeah, so that means that what if you assume just the optimistic scenario for this search, for the collider search, with 100% branching ratio, then there is just a small window that we can probe, and is close to the Z mass. But what happens is that you get too many events, and it's very hard to distinguish from this singlet from just the Z. Yep. Oh, here. So then this, what this says is that, so the collider line, if you increase the energy, these lines will move in this direction, closing the gap. Or if you do more precise measurements, like at the FCC-E, one of the stages, you move this line to the left, also closing the gap. Yeah. So then it's interesting then how, so the muon collider it can probe the entire window, but you can also do the same with FCC-H8, a combination of FCC-H8, FCC-E. Yeah, so it's good. And here's the vector. Then yeah, basically the LHC already excluded the optimistic scenario, the 100% branching ratio. And for high Lumi, we have, I guess, just one patch open, roughly the mass of the Z, and for very light vectors too. Yep. So in case you have any questions. So are we going up to like 8:30, Raymond?
Yes. Yeah. So you have about 20 minutes. Yeah.
Okay. So then now for the Electroweak scenarios, we did not check into hadron colliders yet, but there is still more to say in the context of muon colliders, because remember, like this maximization exercise of for the masses of the new particles pushed us up to 100 TeV, and it is only when you include these ingredients that you bring that scale down to 10 TeV. Yeah, but these are extra assumptions that may not be there, right? But then The question now is like, what happens if what you have is the max surface and nothing else? Yep. So there are indirect signatures that you can look for, and there is an example by Paride and Dario. So you have you only care about the dipole. Just the dipole operator. Look at the coefficient. It's fixed by G-2. You can get the cross section of Higgs gamma. Right? The dipole, you have two muons, Higgs and a gamma. So just collide the two muons, produce a Higgs, produce a gamma. This is what you get. Yeah. So what they see is that if you want, you only want to see a deviation in Higgs gamma. The background for you is a Z gamma. Then if your Higgs goes to two bottoms, and you have to distinguish from a Z going to two bottoms, and you can do that with some efficiency, and also within some angular region, you push up your efficiency a lot. So then what you need is a 30 dB muon collider to see this. This is in the minimal scenario where you only have the dipole. If you have extra ingredients, like all the operators, you would need less energy. Yeah. So then this is a good idea. Now let's look closer to this loop. So the loop that will give you the dipole, looks like this, and then you get the Higgs, the gamma, and from here you get the dipole. Yeah. But now, oh no, wait, yeah. So in the context, so this is just from the operator, right? The Dario's and Paride's work. But then I put this in the context of the models that we wrote. And yeah, we can see here, calculate the boxes, calculate the cross sections. And you can see from here, right, that you can split now the amplitude into left, right, plus right, left, and then the left, left, plus right, right. Because those projections will choose operators, right? The dipole will be the left, right. So you see the line of the cross section to be close to the 0.7 attomars that Paride and the others quoted. Yeah, that's the number you get. At 30 TeV muon collider. Yeah, if you now bring the energy down, that contribution also goes down. Yeah. Let me just bring up again that the cross section goes with S. Yeah. So good. So we can see how you can see these 0.7 attomars coming in the context of the Electroweak scenarios. Yeah, but now go back to the loop, and instead of having a photon, replace that by another Higgs. Yeah. So you gain because now in the cross section, when you square this, you're going to replace the factor of alpha by kappa. But also remember that kappa is not dimension full, is a trilinear Higgs scalar 1, scalar 2 type of coupling. So that means that you also gonna replace so in the dipole you have what? You have F mu nu, so you have a derivative that turns into, when you square, turns into a factor of S. Now you have dimension full, the kappa. Now you don't have that factor of S anymore. Yeah. So you got flat or almost flat cross section in energy, and then so the cross section is sizable. You remember you're replacing a factor of alpha by something that is large, but then you say it's large, but it's because we are in the max surface, okay, where kappa is large. Yeah. So if you look at standard model cross sections for Higgs and ZZ, at 10 TeV, well, this thing keeps appearing here. At 3 TeV, you get 10 to minus 2. I did not find the values for 10 TeV, but then yes, So the signal is comparable to the backgrounds that we have calculated, or I guess these people have calculated. Yeah. Now, if you, let's say, fix to some energy and see how the cross section moves along the max surface, what do you get? So you see this dip, and it correlates with this dip in the center of the surface. What happens is that in the diagonal, remember that kappa is a factor that comes in this interaction. So kappa controls the splitting between these two, the eigenstate that you get after mixing A and B. If you are in the line, that means that the masses are the same, so there's no splitting. So kappa is minimal in that line. But then at some point, kappa is so small that you don't get the G-2 value. There's no way. So that means that this line, it's not that this line doesn't keep falling, it just stops. Okay, you don't get G-2. So then this is more complication because the cross section decreases a little bit, but it's okay. Still, you get sizable cross sections. Yeah. So now you can see the effects in the Higgs. But if you are at the max surface, where kappa is large, where all the couplings are large, but now the problem is that means that you can then decrease those couplings, find a surface that is not the max, but still you're outside of direct production of these new states, right? There's some middle region that is tricky, right? That, let me call it the Nimer zone. So what you have is a 10 TeV muon collider. Yeah, so in the mass of the new physics, if it's below 5 TeV, then yeah, per-produce it, you got it. It cannot be beyond roughly 100 TeV because you enter in trouble with perturbativity. Below 10 TeV, there is some scale that's model dependent. I'll show you examples for the models with two scalars and one fermion, but then for the models with two fermions and one scalar, that's going to be different or not. And then, but then you know that the Higgs that means the Higgs signal will give you some deviations, and then that means that you cannot be at the max surface. You have to shrink it. But then there is this middle region where you're gonna be in troubles. Okay. If you have a 30 TeV muon collider, there's no middle region because Higgs-gamma production will see a deviation. Yeah. Yeah. Now we gotta put this into the context of a given model to be more precise in quantifying this. And when I was engineering these models, or when we were engineering these models, I told you I want to be perverse and just let me put the ingredients that we need in order to push the scale as high as possible. But then, so recently, like studying potential UV completions, actually you could realize this in a leptoquark type of scenario, but that falls in the category of having one scalar, and the two new fermions are actually the top quark. So imagine you got two fermions, but there's the top quark, one chirality, and then the other chirality of the top quark. The top mass gives you the chiral flip. You have the leptoquark inside the loop. So it's a leptoquark that will talk to the top quark and the muon. Yeah. So then, depending on the flavor structure that you arrange for this leptoquark, if it talks to first generations somehow, you can you get constraints from meson decays. So these constraints will push your leptoquark mass very high, but 100 TeV is already very high for that. So you got these leptoquarks living at 100 TeV. They will give you this for couplings of couplings larger than 1, couplings of 2. If you bring down the coupling to 1, your leptoquark will be about 40 to 50 TeV. Yeah. Yeah, and then the Higgs production will bring you even lower. So again, so this line here, you got to put it in the context of models. So yeah, just to summarize, so we did this exercise of looking at the most perverse BSM scenarios for this G-2. We found the scale of 100 TeV as an upper ceiling. The idea is that with indirect signatures of Higgs+gamma, 30 TeV collider will see deviations, so it's good. But then, in the meanwhile, hadron collider and a combination with Electroweak precision measurements will cover what we call the Singlet Scenarios, where the ceiling is at 3 TeV, but then it is good to see how the Muon collider and FCC will complement each other. And then we found this Higgs production that will give you constraints at the max surface and define this Nimer middle ground that would, so far, that can only be covered with a 30 TeV Muon collider looking at a Higgs+gamma. But then we keep on investigating to see what happens with this middle ground. That's why stay tuned. Yeah, so then just thank you very much.
Thanks a lot for the nice talk.
Thank you.
So I have a question about just the Muon, the 30 TeV Muon collider. I mean, what's the time? I mean, where's this going to be built, and what's the? I mean, what's the current thinking about it? That's all I meant.
Yeah, so 30 is actually not actually, and so it's not even a consideration. It's like, so the highest we have, or the highest that the Muon collider collaboration has discussed is the 10 TeV as a reasonable or achievable goal, with that 3 TeV machine as a first step, because you scale up in energy. So
this
far,
is
yeah.
This is supposed to be built at CERN. That's the only site, right, that would build this place.
Yeah. Yes.
I see.
Yeah. First 3 TeV and then 10. Yeah, but the time frame, and I'm not really sure about this.
Yeah, let me say a few words regarding Tony's question. Of course, the U.S. side, U.S. used to be leading on the Muon collider research, right? It's just the last SNOMAS, they unfortunately dismissed that accelerator program. Now there's renewed interest in the U.S. side to pick it up. SNOMAS is about to put out, the Muon collider forum is about to put out benchmark scenarios to consider. I forgot, 10 is definitely in their map, and they maybe want to discuss 30 as well. But the reason for 30 to come into people's mind is very simple, right? If people can claim the weak field plasma accelerator can accelerate electrons to 30 TeV, why can't you think about the Muon collider? That's for sure. You can do that too. So they can even discuss about sometimes people even discuss about 100 TeV Muon collider. That is to the current technological understanding totally impossible, but some people want to be more optimistic. So
you're saying, so Zhen, you're saying that this could be built in the US?
That's secret hope of several people, not several people, a sizable community. That's why there's a US-based forum formed, and there's a lot of people participating.
Yeah. So then, but then, like for LHC-like type of tunnel, right? You can achieve up to 14 TeV or so with current magnets. That's what they say, right? Or something.
Yeah. In the last round of planning, 2013 planning, their claim is use half of the Tevatron ring plus another half plus some linear acceleration component. You can make 10 TeV even on Fermilab side. But for now, people don't talk about those things too much because this is such an early stage. People are still trying to not talk about the set so it's a muon collider international collaboration. However, the CERN-based muon collider collaboration made it explicit that where our R&D also should be made in the international ground that is also readily portable to other countries if there's a interest and funding available for other countries. So CERN didn't possess a muon collider option as their own, has to be on their own land from the very beginning.
So Rodolfo, I have a question about your discussion about the lepton quark. You said that they have to be constrained to be pretty heavy, and I'm just wondering what the advantage of using the lepton quark model is.
Oh, because they can come from some unification scenario that maybe you care about unification. They will be there.
I see. So you mean it's just more theoretically motivated?
Yeah. Because when you talk about these models and 100 TVs and stuff, like people ask you like, hey, what is the UV for for that, right?
Yeah.
And yeah, you can find one in the unification.
I have a question. Hi Rodolfo.
Oh, hi, Max.
So since this linking to G-2 is a very speculative thing, did you try to also link to others speculative anomalies such as, I don't know, a slight muon deficit in LHCb, or perhaps what was that? BB bar mu bar excess at the LHC. There was like a 30 Jen, correct me if I'm wrong, 30 GeV excess at the LHC or something like that.
Not official, by the way. That normally is not official.
Well, I've seen several theory papers discussing it already, right? Official, right?
So not the ones you mentioned, but by the time we were doing the RK anomaly, B2K mu mu, we got scooped. So,
okay.
Yeah.
Okay. So, but aside of priorities in getting future Nobel prizes, this is the right thing to do, right? I mean, like to link to.
No, but wouldn't there be also motivation from composite Higgs or SUSY as well, right? Or not? I mean, I imagine people were studying muon collider before these anomalies as well.
Sure. Yeah. So general BSM physics are
it would be
motivation. There are studies on that. In fact, there are studies, but not so many. So we don't have a complete picture on those, but we just have general discussions like, stop rate is half the central mass energy, blah blah blah. This kind of simple argument. For composite models, there hasn't been any complete study on this yet. There are groups working on that,
but when you say complete study, I mean, you mean on this 30 TeV concept? Because I know that there were studies before, right, on 3 TeV or earlier, I thought.
Yeah. But you see, the 3 TeV is not that a compelling case for muon collider, in the sense that electron collider can already get there from clique concept. Why bother with muon collider? So muon collider really come into play when you start to confidently say, I want a 10 TeV and above, and then you discuss physics there. So 10 TeV physics has not been laid out nicely yet. Okay, there's a muon smasher guide. We attempt to say something, but no real study.
I see.
I see. So then, Jen, you suggest that the first stage for the muon collider would be then a Higgs factory. So we get the Higgs width, and then we scale to 10 TeV. That's what you're saying.
I'm not claiming that. Just to be clear, although people misinterpret me, always say I want 125. I say people don't understand the 125 physics, the muon collider potential. I'm just evaluating that, and I show that information is complementary, not let's say completely throw other Higgs factor out of water, and it's such a later time scale. So I'm saying I give you the physics rich. It's up to accelerator physics to decide whether that's too much cause of a detour or you should directly go to high energy. For me, obviously you want high energy, okay? I don't want to spend extra time on the low physics, but nobody knows what's the physics rich. So I'm finishing evaluating that.
Yeah, but imagine that experimentalists suggest, you know, that there's usually like a low energy stage and then they ramp up, right? You know.
Yeah.
So then the low energy stage for a 125 would be then more motivated than a 3 TeV.
Yeah. I'm sorry. I cannot say that. Just to be clear, I don't say 125 is more motivated by compared to 3 TeV. They are just different physics. One is Higgs physics specific. The other is generic new physics at the TeV scale, right? From electroweak process. So it's a different physics. Yeah, but I have two physics questions for you. I missed your beginning part due to other meetings. So in the middle, you showed the LHC sensitivity to your singlet realization, etc. What's the target space to explain the anomaly?
What is the what space?
Later on, you have one or two more slides here, right? So what's my goal to probe G-2 here? Is there a line or a band I want to probe, or there's
yeah, no, the coupling is fixed for each mass of the singlet. Yeah. So
that's really the solid line tells me what's the optimistic reach for G-2 and the conservative reach for G-2 for the given mass, right? When they cross the line. Yeah, good. The second question is, when you define this nightmare region for tensor TeV for singlet mass, let me just understand where the small kappa come from. Is it come from some degeneracy in the particles in the loop that will get enhancement, or coming from something else?
This is in the Electroweak models.
Yeah, you know, later on you say there's a nightmare of 10 TeV. So what's the origin of the small kappa for this model? It's really just for this particular model at this certain scale you have. Where does smallness come from? Smallness.
Yeah. So no, the thing is that even in the models where you have two fermions and one scalar, so let's switch here, right? Even in those models, you can do the same thing of removing the photon or replacing the photon for a Higgs, and then you're gonna do the Higgs search. But what I'm saying is that so the cross section is basically flat in energy, and it's sizable, so you can constrain, you get deviations. But that this only works when these couplings are maximized. So when you are at the max surface, right? You could then find a regional parameter space where you reduce those couplings, the masses also go down, and it's this middle region over here that I'm calling Nimer, but I'm calling it because I have a 10 TeV muon collider, right? If I have a 30 TeV muon collider, there's no, because you can do Higgs+gamma. Yeah.
So it's a nightmare because I cannot access the Higgs+gamma yet, but the Higgs is minimized. Is that the degree of freedom in your modeling? It's nothing to do with G-2 in some sense, because that's one additional parameter you are tuning down. Is that right? Yeah. So it's a design nightmare, not the real nightmare in some sense.
Well, if you have a 10 TeV muon collider, let's say. But the thing is that we don't. I mean, why would those live at the max surface? Right? They could live somewhere in between, so it's a possibility.
Sure. Okay. Yeah. Thanks.
Yeah. Thank you. Great discussion. Thank you.
Any other questions for Rodolfo? All right. If not, then let's thank the speaker again.
Yeah. Thank you.
Thank you.